All right, so let's get this on the road. All right, so if you don't know me by now, I'm Ryan Dougherty. I'm a PhD student here, and I'm going to be talking about something that's been happening in terms of my research area, and I like the title because it really does convey both parts of the talk, the first one being today and the one being a week from today. The post-optimization word is the word that represents something in my research, and optimizing is the part that has to do with optimizing the implementation of the research. And so the post-optimization part, I'm going to be talking pretty much exclusively today, and optimization is next week. So just a little bit of background on myself, because I want to motivate the problem a little bit, and then I'll tell you a little bit about what I actually like researching. So I'm a PhD student here, and there are three primary interests of research that I like doing. I'm going to talk about two other ones, but the third one will be the one that will be the rest of the talk. So one area is what is called computational complexity, which is I have some problem I want to solve, and with respect to some measure, be it amount of time used or how much space is used, or I don't know, how many disk writes are done, I want to figure out how much resources do I need to actually solve the problem. And this involves questions like P versus NP, one of the most famous problems in computer science, among zillions of other problems. And it's a very open field, one of the largest fields in computer science today. Another part of research I like doing is, suppose you're talking about a road network or a computer network or something like that. We typically like thinking of these as graphs, if you've ever studied a graph in computer science. And we want to say, okay, what is the shortest path between two different nodes? Or maybe what is the average length between these two nodes, or something like that. But maybe in the real world, some of those links are going to fail with some probability. So maybe if I tell you, okay, each of the edges is going to fail with some fixed probability, or maybe a probability for each of the links, can I figure out, okay, is there something that I can say about the network? What maybe is the expected shortest path, or maybe is the graph even connected at this point? And so this is a very non-trivial area of research, and I like it very much. But the one I'm going to talk about is testing large-scale systems. So as we're getting involved with larger and larger amounts of data, we need larger and larger systems to be able to cope with all this. And so we have to absolutely make sure that these systems are correct with respect to use cases and all that stuff. And so obviously, if we have a lot of tests, then I can't test every single thing that we could ever want to do. So we have to scale back the testing somewhat in some respects. And so this area is basically about trying to understand the trade-off between how much should I test and how much computation time am I allowed to do for testing. So here are just some goals throughout both talks and what you'll see throughout them. So for goals, I want you to be able to understand a real world research problem. So this isn't something that's like entirely theoretical. This really is used in many different software test suite generation programs. One example is called ACTS, which is a combinatorial test suite, is what the acronym stands for. But we can also want to think about, I have this problem I want to solve. Could we think of some interesting questions that might be worth pursuing and try to understand this problem a little bit more? Another one is, I get this statement a lot, that math is not useful for computer science. Why am I taking math courses? I just want to be able to program. But I want to be able to convince you that math really is important for computer science. And there's actually a very often used phrase called computer science is just applied math. And in many respects, including the one I'm going to show you, it really is just applied math. So that's another thing I want you to see. And in the second half of the talks for next week, I want you to get some general programming guidelines. So I'm going to be talking exclusively pretty much about C++, but they're going to apply to general programming guidelines that I think would be very important to consider when you have a problem like this to work with. So what are you going to see? About 40% of the talk, so most of today, is going to be talking about this research problem that I'm going to talk about. A little bit of linear algebra, so if you know linear algebra, great. If you don't, that's perfectly okay. It's not a necessary thing here, but linear algebra is used here, so that's where the math part comes in here. And then the other half is about guidelines for past performance, both in C++ and in general. So just a description of the problem. So we have this large-scale system that we want to test to make sure it's correct. And what we want to do is, with respect to some tests, we want to measure, okay, if I feed it this particular input, I'm supposed to get this output, this input, this output, et cetera, all the way through. I want to make sure that this system is correct and not have to dive too deep into the actual intricacies of the system. And so what we may want to consider is what is the absolute minimum number of tests to meet some adequate testing requirements. And so obviously we can't test everything because I've heard of several examples where something similar to Word, where the preferences pane has 100 different checkboxes, and we would need to be able to check all 2 to the 100 different possibilities. And if we did that, it would take longer than the lifetime of the universe to do that. So we clearly can't test everything. And we can't test nothing either, right? Because if we just test nothing, then we can't say anything about whether a system works anyway. So there's got to be some middle ground that we have to consider here. So we need to have some trade-off, as I said earlier. So what I want you to think about is I have these components and they're going to be interacting with each other. So what I'm going to assume at the outset is that all unit testing is done. So each component by itself works perfectly fine, but there may be some problems when I combine different components together. So if I just want to test whether a certain different combination of tests of different components actually causes what is called a fault or an error. And it seems intuitive that if you have a lot of components interacting together, it seems intuitive that if I have a bunch of components and then I add that are working together, but then I add one more, it's very unlikely that that one more addition is going to cause a fault. And there's actually a lot of empirical evidence to suggest this. There was a paper around, I think 14 years ago now, 15 years ago, that empirically studied different large-scale systems and was able to find that if I test up to 6-way interactions between components, then I have found within an error about 99.9% of all bugs that are present within the system. So I don't need to test a whole bunch of components interacting together at the same time. And yeah, that's what I said earlier. It seems intuitive that a small number of components is going to cause a fault instead of a large number when they're all interacting at the same time. So what we want to do is we want to model interactions of components in a system. All right. So just a motivating example, just to get some real practicalities here. So how many of you have used the sort command in Unix? Okay, a few of you. So obviously Unix is a really widely used system. It's in every single Mac you ever have. It's every computer that runs Ubuntu. Any Linux system at all is going to have this command sort. And I'm sure Windows has a similar one. But this is a very important command, right? I want data to be absolutely sorted, and I don't want any possible input to be unsorted if I run this run it through sort. And just letting you know, there are 18 execution time binary flags. So I can set this particular option on or off, this particular option on or off, etc., and I have 18 to choose from. How can we check if a certain combination of flags works? So if I have a certain combination, I can just run it through sort, and then I have some tests where I have the input that is given and the expected output, and then I just match the output and see if it actually is the same. But the problem is, if I test every single combination, then I have 2 to the 18 different possible tests to use, which is around 262,000. And although 262,000 isn't that big, I may need a whole bunch of tests. If you instead change this to 3, instead of like having binary flags on or off, I have 3 different options for each of the flags. It was, I calculated it today, it's around 350 million. So there's, this gets out of hand really, really quickly. So I definitely need something better than this. But here's something that I can tell you right now. If I wanted to look up to 6-way interactions, how many tests do I actually need? So I'm going to tell you all 1-way, 2-way, 3, 4, 5, and 6-way interactions. What is the best known number of tests that I need to accurately test this? Well, for one, it's pretty obvious. I can have all the options set to on, all the options set to off, and I can't do any better than that, right? I really do need to test all those, both of those possibilities, and this is optimal. If I had 2 choices, you can actually do this with 8 tests, and this has been proven to be optimal, and this was proved by people named Spencer and Cantona and Kleitman in the 1960s independently, and they were able to show that this was optimal. But as soon as we get to 3, we don't even know if it's optimal yet. I can do all 3-way interactions, so pick any 3 components. I need to see every possible way to test those 3 components. I can do that with 18 tests, and that was found in 2002. If I go to 4, I can do it with 36 tests, and that was, the best known was found only 5 years ago. 5 components, this is actually not correct. The real number is 99 here. But the best known was found only 2 years ago. So this really is an ongoing research problem. And all 6-way interactions with 260 tests. So the number of tests is growing, but it's nowhere even close to 262,000. So this area of research is called combinatorial testing. I'm finding the minimum number of tests to test a combination of components. So, and that was only found 2 years ago, which is pretty amazing. All right, so to talk about how interactions are going to work together, I need to tell you what a covering array is. And so a covering array is going to basically model this idea of components interacting with each other. So I'm going to have 4 integers, n, t, k, and v. So what a covering array is an n by k array. So I have n rows and k columns. I promise I have an example. So hold on to your hats for that. N rows and k columns, and each of the entries of this array is from a v area alphabet, as it's called. But you can think of this as 0, 1, 2, 3, up to v minus 1. So there are v possibilities for every single one of the entries. But for every t column, so t here is called the strength in the literature. So whenever I say strength 3, t equals 3 here. So I pick any t columns I like. I need to check every single possible t choices of columns. And I pick a particular test vector. So you can think of R right here as being the settings to those flags, like in the sort command from earlier. And what I want is, I say that this array covers this particular test vector if in those columns you see that test vector in those columns. So it really is testing the interaction of that particular test vector. And we say that it's a covering array if no matter what choice of columns, of t columns that you pick, you have every single test vector appearing in those columns. So those columns are covering in those t columns. And the reason why you want this is you can think of the components, these k components, as being the components of your system. And for any possible choice of this t parameter, I have these t columns covering. And we can think of the v as being all of the possible values that can be given to a particular component. So you may think, well, different components can have different numbers of possible inputs, and that's definitely true. But I'm going to focus on what is called the uniform case here, where every single component can have the exact same number. And you can actually work this out yourself. You can pick whatever components you have, and whatever has the maximum number of possible inputs, just make every single component have that number, right? Because If you're going to be covering on fewer on possible values, then you're certainly going to be covering on more. All right, so here's an example. So I claim that this is a covering array with n equal 13, t equal 3, k equal to 10, and v equal to 2. So what you should check here is that, do I have 13 rows? And that's pretty easy to check. I do have 13 rows. Do I have 10 columns? And I certainly do. Is every single entry in this array a 0 or a 1? And that's pretty easy to check. So the pretty much non-trivial thing to check is, no matter what 3 columns I pick, I better see 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. All 8 possible 3-length binary vectors. So I'm going to let you guys pick any 3 columns that you want. And through the magic of PowerPoint, I can figure out what 3 columns you're thinking of. Okay? So are you thinking of your 3 columns? All right, you definitely picked those 3 columns, right? Obviously you didn't. But I need to check this for every choice of 3 columns, obviously. So I pick here, and I want to see, do I see a 0, 0, 0 in there? And I definitely do, it's in the top row, but I definitely see it in the bottom 2 rows also, right? The colors are not that good here, but I see 0, 0, 0 3 times, that's okay, as long as I see it at least once, which is perfectly okay. As long as I see it at least once, we're good. So we see 0, 0, 0. Now I gotta check 0, 0, 0, 0, 1, and I do, it's in the 5th row. I see 0, 1, 0, 3 rows down. 0, 1, 1, I see twice down there, so that's good. 1, 0, 0, I see there. 1, 0, 1, I see. 1, 1, 0, I see. And 1, 1, 1, I see. So am I done checking that this is a covering array? No, I'm done checking these columns, but I'm not done checking the whole array. No, I need to check all other the 3 choices of columns, right? I need to check, like, say, the first column and the last 2. I need to check every single 3 choice of columns. So, but I'm only done in these ones. So, real question is, essentially, I want to find a covering array with the minimum number of rows, which corresponds to the minimum number of tests in the system. So, in fact, with this array that we have here, the best known is 12 rows. So the array that I showed you is not even minimal with respect to the number of rows. So I can actually remove a row. And another thing that's even more interesting, I can even extend the column with still only have 12 rows. So this is actually pretty interesting in terms of figuring out what is the actual minimum here. And for small covering arrays, the best known that is proven optimal, other than that Kleitman and Spencer one I told you about, is done through brute force. So even with this array here, there are 130 entries in here. To do it brute force, I need to do 2 to the 130 things, which is definitely not feasible. So it's actually a very interesting question. How do you actually find and actually prove whether something's optimal, or actually find something that's even less than the thing that you currently have? So what is the real smallest? And can we prove lower number bounds? So most of the bounds that are known are based on upper bounds, like the biggest parameters are below a specific value. So we're going to define a parameter called can of TKV. So this is just that minimal number of rows thing. So it's just the smallest n for which a covering array with that many rows exists. So here we showed that 3, 10, and 3, 10, 2 is less than or equal to 13, but I claim that there's one with 1 less row, and that has 12. So it's at most 12 there. The only known exact values, which are that paper I told you, is when t and v are equal to 2. If I move t to 3 or even v to 3, we don't know the optimal in general for all values of k. There's some values that we do know optimal, but we don't know them in general, which is a really big problem. If you're curious, the growth is approximately log k. So with respect to t and v. So I need to have v to the t rows, but I might not get exactly v to the t, and then the multiplicative factor is log k. So in terms of asymptotic growth, is based on the number of columns, but we don't know exact values. This only gives us asymptotics, but that doesn't really tell us very much. And there's some other computational problems, like if I have this array, I need to check whether it's a covering array. I need to check every single possible choice of t columns, right? But that's a very big problem because I have to see v to the t things. So in the array that I showed you, the example, I needed to see 2 to the 3 things, which is 8. So I can't have any less than 8 rows, for sure. But I don't know this in general. But if I have a very large t, say 6, and v moderately large, then that to the 6th power is already huge. And we also have to check every possible t choices of columns, which is denoted k choose t. This is actually very, very large if you have anything that's even moderately large for k and t. And just to give you some numerical data, if you have k equal to 6 and v equal to 25, the smallest array that you can have is in the tens of billions of rows. So this is absolutely a huge problem, and we can't verify this in general because it would just take too long. And so we have to do v to the t times k choose t work because I need to see v to the t things for every choice of the t columns. So I need to do this amount of work, and that takes a really long amount of time. Another example. So if we had 3, 10, 2 before, but if I increase the strength up to 6, I need to see 2 to the 6 things because it's at least v to the t, which is 64. The best known is 116. And if I increase the number of columns, the difference between the asymptotic best and what is really known is much larger, sometimes even 10 times larger than what we expect it to actually be. So that's a really big problem. And so the research idea is, let's try to make larger covering arrays from smaller ones. And another research idea is, okay, I have this covering array, I want to optimize it somehow. Maybe by eliminating a row or maybe eliminating a column, I need to optimize it in some way. Okay, and some other problems. If I wanted to make a covering array smaller, I would want to eliminate a row if I can. But how would I even do that? And that's the idea of post-optimization, which I'll define in a second. But how would I even do this without trying all possibilities of the other entries in the covering array? And another idea is, let's have a smaller representation of a covering array if we can. Maybe we can have some really small compact thing that somehow can be converted into a covering array, and that this small thing is covering in a sense. And if I blow it up, I guarantee that the covering array it generates, it really is covering. So I don't even need to check the covering array at the end because it'll just be too big. All right. So several techniques to get around the computational problems before I get into the smaller representation. So another idea you might try is, okay, I have this covering array that already is covering. I verified it already somehow. And I add another column, right? That seems like an idea that we might want to try. And the good thing about this is that among the columns that were already there, they already cover. So I don't even need to check among those columns. The only things I need to worry about are with the new column and t minus 1 other things. So I only need to do k choose t minus 1 work here instead of k choose t. And I ran a few examples when I was doing some of my research, and the difference that this makes is sometimes 100-fold difference. And so this is actually what is called random extension, and is actually responsible for some of the best covering arrays we know today, being able to just keep adding columns randomly until some stopping condition occurs. Yeah, so we repeatedly add a new column, a random one, until we stop at some point. Maybe it takes too long to add a new column, and the covering array wouldn't be covering at that point. And then another idea is, okay, let's have two or more smaller covering arrays, and then I make this really large thing that's covering if and only if the small things are covered. So I can check the small things really easily, and then I can just glue the pieces together to build larger ones. And this is what is called a recursive construction because I'm recursing on smaller covering arrays. Just like a recursive problem that you would solve normally, I'm just recursing on smaller things. Some other techniques you might want to try are, instead of adding columns, let's add new rows, right? Because maybe I can get away with adding new rows to an empty array until the array becomes covering. And this is what is called the density algorithm. Again, this is actually what is, some of these arrays are best known today still. And there's a few results that you can show that you can get better than the average rows as you're adding them, because maybe you're trying to add a random row and it's completely garbage. You didn't even need it ever. So there's a way to actually get better than the average here, and it actually gives really good results in general. Yeah, it performs well in general. And then another technique is, well, maybe I don't want to add new columns or add new rows to an empty array. Maybe I can take an array that's probably not covering and then just permute the entries or change the entries in a random way somehow. And then hopefully I can get a covering array out of that. And that's actually one of the main parts of this research that I'm going to tell you. So how do you even do randomly? How do you even check how do you even choose what entries to change? And so there are many techniques here that I'm not going to go into, but I'm sure some of you have heard of just doing random search or genetic algorithms or simulated annealing. Simulated annealing was actually responsible for some of the best known arrays with the sort one I told you about. The ones from 2015, those are with simulated annealing. So it's pretty amazing that the best results that are known are purely based on random search. So we actually don't know if the best known arrays are based on random things, but it seems like in general that they are. All right, so any questions so far before we dive really deep? All right, so before I actually talk about this really small compact representation, I need to tell you about permutation vectors. So this is where your math hat comes on and your programmer brain comes out the window. So think of a prime or prime power. So ignore prime power because the math gets really complicated at that point. So just think of any prime number, so like 3, for example. And I do have an example here, so if you don't follow along, I have an example. And so let something called a finite field of order V. And so what does this mean? So only think of primes. So what this means is that I'm just going to do addition and multiplication mod this number V. So if it was 3, then maybe I can think of 2 plus 2, well that's 4. If I take the remainder of when I divide it by 3, that's 1. So, and multiplication works the exact same way. So I can think about these remainders, and that's what the finite field of order V is, when V is a prime number. And so, so I'm going to call something called BI, which is just the base V representation of a number. So I can think of, if V is 2, then this is just the binary representation of a number. If it's 3, then it's just the base 3 representation, nothing fancy there. And then what I'm going to do is this matrix A is just going to assemble all of these VIs in one matrix. So V to the T, so V to the T rows and T columns. So each of these BI has length T, so each of the rows is going to be a BI. So I have an example, don't worry. But that's how I'm going to assemble these things. And I'm just going to think of any vector that you want over this finite field. So if it was, let's say T is equal to 3, and V is also 3. So I want a vector, so an array, you can think of it, of length 2, where each entry comes from 0, 1, 2, 0, 1, 2, and 0, 1, 2. So I can think of, say, 0, 1, 2, that's some vector of length T minus 1 over the field. But I'm going to add first entry to be 1. Okay, so pick T minus 1 things, add a 1 at the front. Okay? And then just do matrix vector multiplication. So this matrix A times this vector that I just made. And all of the addition and multiplication is done over the field, like I told you earlier. And so this H star thing, that's what I call a permutation vector. So don't worry, I have an example, so don't feel lost yet. So yeah, here's the example. So let's choose T equal to 4. So I want, remember, I want T minus 1 things with a 1 at the front of it. So I want to look at all 3 length vectors over 0, 1, 2, 0, 1, 2, 0, 1, 2. And so our BI are B0, so base 3 representation of 0 is 0, 0, 0, then 0, 0, 1 for 1, up to 15, so I had an intermediate value. This is 1, 2, 0 in base 3, and then 26 is 2, 2, 2. All right? And then, so our matrix A is just, I just assemble these BIs as rows. Nothing fancy there. And then what I'm going to do is this, I'm going to think of any vector I like. So 2, 1, 2 for this case. And then now I'm going to think about the vector, matrix vector multiplication. So H plus is 2, 1, 2. And then with our matrix and vector, we're going to add and multiply mod V. Don't worry about non-prime prime powers here. So think of the first entry of H star, the 0 up there, is going to be the first row of A times the column 2, 1, 2. So 0 times 2 is 0, plus 1 times 0 is 0 again, and 2 times 0 is 0. So 0 plus 0 plus 0, I think is 0. Mod 3 is still 0. And then the second one works the same way. So I want to work through the base 15 one. So 2 times 1 is 2. 2 times 1 is 2 again, so I add those. And 0 times 2 is 0. So 2 plus 2 plus 0 is 4. 4, when I take the remainder mod 3, that's 1. So I put a 1, oh, that should be a 1. It was in the fixed slides. but that entry should be a 1, corresponding to the 15th row. And then I just do this all the way through. Okay? So what I'm going to think of is I have these vectors, these column things that I'm multiplying by this A matrix. Each one has length t with the corresponding permutation vector. So I think about the matrix vector multiplication. I think about what all these results are going to be. So I'm just going to assemble the original vectors, these t-like things, before the multiplication into a matrix, H, which is a square matrix because it has the same number of rows and columns. And if I multiply this out, if you work through the details, it's a matrix which has v to the t rows and t columns, and each of the columns is those permutation vectors. So I can just assemble everything all in one matrix and then just do matrix times matrix instead of a bunch of matrix vector multiplications. And we say that these t permutation vectors is covering if the resulting v to the t times t matrix is a covering array. Okay? That's what I'm going to define these vectors to be covering for. And don't worry about the definition too much. A covering perfect hash family, so this is the real research that I'm studying here, is, so I have nkvt again. So it's still an n by k array, so that doesn't change. Each of the entries is these t-length vectors over 0, 1, 2, 3, up to v minus 1. So instead of just a single entry, it's going to be t things. And for every possible t choices of columns, they cover according to the definition up there. Okay. So, but instead of thinking about making covering arrays, we can think about these in a different way. So a theorem that was proved just last year was this square matrix of these t permutation vectors is going to cover if and only if this matrix has non-zero determinant. It's a non-singular matrix. So this is where the linear algebra comes in. So instead of thinking about making these big covering arrays, these v to the t things, I only need to check a t by t matrix, which is much faster than having to actually make the array first and then check if it's a covering array. So this is actually very, very helpful for us. And something that'll be really helpful in a bit. If a covering perfect hash family exists, then I can basically blow this up into a large covering array, and that exists. And the idea is, what we're going to do is take this permutation vector, this very long v to the t thing, and stick it into an empty array over and over again, and then I get a covering array. You can check the details for that. And you may think, well, what the heck is this if you have v to the t things and you're stacking them on top of each other, you have n times v to the t. Well, what is this minus v plus v thing? Well, if you check through the details, you're going to be adding, for each one of those n v to the t things you're going to be adding v constant rows, which means that every single entry among those columns is going to be the exact same thing. Well, if I have two identical rows, then there's no point in having multiple copies, because if it's covering here, it's covering here also. So there's no point in having them. So, but I need to have them. So I'm going to eliminate all of those constant rows and then add only one copy back. So that's where the minus v comes in, and then I just add v more rows at the end. All right. And in general, checking non-zero determinant is much faster than actually checking a covering array that has v to the t rows here. All right, so here's an example. So I claim that this is a covering perfect hash family with 2 rows, 6 columns, 3 symbols, and strength 4. So we have to check 2 rows, easy. 6 columns, also easy. Are each of the entries of length 4 minus 1, which is 3, and we can easily check that. So now we need to check for all 4 possible columns whether they cover or not. So whether there is some row that actually covers. So again, I want you to pick 4 columns. Are you thinking of 4 columns? All right, so again, I'm going to guess which columns you picked, and those are the ones you picked, right? Okay, so now what I'm going to do is I'm going to iterate through the rows and then check, does this row cover? Does this row cover? Which means, does this matrix that I assembled cover? Is it a non-zero determinant? So I'm going to check this first row. So what I'm going to do is I'm going to literally copy and paste these 4 entries as columns. So I'm going to rotate them and add a 1 on the top, because I need to have a 1 in the first entry. Yeah, I need to check whether this is non-zero determinant. So the first row, so the 4 columns, other than the first row, those were the 4 entries of the matrix that I looked at earlier. And if you actually run through the numbers, this has determinant 1, which is not 0 mod 3. So those 4 columns cover. I only need 1 row for this to work. Instead of having every single row, I need at least 1 row to work. Okay? Therefore, these columns cover, and obviously I need to check every choice of 4 columns. Okay, so you may think, well, that's just a ton of math, right? That doesn't have any real world performance. So I want to convince you otherwise. So remember CAN-TKV, which is the smallest covering array, this big thing I want to make. So in this case, I have strength 5 and 4 symbols. And the horizontal axis is k. And note that the axis is logarithmic, so it's 1, 10, 100, 1,000, 10,000. And I'm plotting the best known covering array before we started working with covering perfect hash families and afterward. So this was before. So right around 10,000 columns, it's around, I guess, 105,000 rows. And if we add covering perfect hash families, it comes down here. So for both small covering arrays and larger ones, I do have a dramatic reduction in the number of rows. And I'm going to do another one, which is even more striking. So note the vertical axis here is in the millions of rows. So we're going to get up to 6 million rows here. So strength 6 with 5 symbols. And so before covering perfect hash families and afterward. A dramatic reduction. It's like even with the larger ones, it's like around 2 or 3 times smaller just by using this simple construction, which is actually pretty interesting. So we might want to consider, okay, let's use these covering perfect hash families from now on and forget about covering arrays. Well, we've got to make these things, but let's focus our attention on covering perfect hash families. And so a question you might think, well, I have these 4 parameters. Can you make a covering perfect hash family out of these, right? I hate to say that the only results that are known are purely computational. There's no like theorems that say there always will be a covering perfect hash family of a certain size. We only do this purely from computation. So yeah, computational methods are only known. We want to have small covering arrays, and they're based off CPHFs. And why would we want to remove a row of a CPHF? Well, remember, if we want to make a covering array, we have n times v to the t things. Well, if I knock 1 off of n, I've knocked v to the t off of the array that I'm going to make. And so instead of removing 1 row of the covering array, I eliminate a whole bunch of rows at once. And so that's the row that I'm going to be looking at here. Many rows will be removed. But how do we guarantee that a row will be removed? And so this is the idea of post-optimization. So what is post-optimization? So the idea is, let's try to make every other row cover other than a given row. So if I have a row and everything that involves that row is covered somewhere else, I don't need that row anymore, right? So an idea is, well, maybe we can have a certain entry being what is called a don't care, which means I don't care what value is in there. It doesn't matter if the CPHF is still covering. I don't care about it. And then some other definitions. Possibly don't care means if you have 2 or more possible values. Flexible set, which is just basically you put all of the don't cares together. But this is just some stuff in the literature, but we're not going to actually use it. Partially flexible set is just putting all the flexible sets together, but we're not going to actually use this. But an idea is, let's just try every single possible value for each of the entries. Like, I have this t-length vector, and I'm just going to try every single possible thing and see, do I ever get a don't care value? Or maybe do I ever get a row that isn't covering? Well, here's the problem. Well, I have t of -1 length vectors, and each one of those entries has v things. Well, that takes v to the t -1 time. The array that I'm going to generate has roughly v to the t size, and I might as well just generate the array itself. Like, this has no use to me whatsoever. There's slight improvements, but it's almost nothing to me. But what we want to do instead, which will be much more efficient possibly, is just randomly change the entries of this CPHF until I cover without a given row. So I'm going to talk about 3 different variants. We're going to only pursue 1. So several approaches. The one I'm going to talk about is uncovered interaction. So let's just say I have some t columns that is not covered. Then I want to reduce the number of these uncovered choices of columns. If I reduce it ever to 0 without considering a given row, then I can just eliminate that row, which is the row that I looked at. You can also reduce the number of columns that are involved in uncovered interactions. So maybe what I can do is, instead of having every column involved in uncovered interactions, I just reduce it to a few. Then maybe if I knock one out, then I can still have a covering perfect hash family. But the problem is, this didn't work once, unfortunately. I'll show results where the first one did work, but this one did not work a single time, which is unfortunate. But maybe it works, but it didn't work for me. But another idea is, well, each column is going to be involved in some number of uncovered interactions. Why not just increase that number as high as possible? Then I can try to eliminate that one column, then a bunch of interactions that are uncovered disappear. And so that actually did give some results, but very few comparatively. You can actually combine the first and the third, but not very much, because they have different goals in what they're trying to accomplish. So we want to reach 0 uncovered interactions, obviously. But the problem is, we made hit what's called a local optimum, which means no matter what change I'm going to make, I'm only going to get a worse CPHF. And maybe the best is somewhere very far away from the one I'm currently at. And so a problem with that is I want to get out of local optimum. It's hard to detect if we are actually in one. And what we'll do instead is, maybe this row that I'm trying to eliminate, maybe it really did cover a lot of things before. So maybe after a certain amount of time, some threshold, I'm going to randomly swap some other row with it. And then maybe we'll try again. Maybe I can get lower. So it helps try to get us out of this local optimum. So here's the algorithm in general that I implemented. This works for not just for CPHS, but it works in general, like for covering arrays and such. So I have this row I want to eliminate, and I'm going to move it down to the bottom. So it's going to be the very last row. And then while we haven't hit a stopping condition, so I currently have this at setting, I keep doing this for 40 minutes, but I've tried different things and all of them give some kind of result that's helpful here. I'm going to calculate the number of uncovered interactions that each column participates in that doesn't involve the last row, the row that I want to eliminate. And so the selection process of what entry to change is entirely random, but it's weighted random, which means that if a column is involved in more uncovered interactions, I want to change that column more, right? So I'm going to weight it based off of how many interactions it's involved in. I'm going to generate a random vector and put it in this column, in every single entry but the last one, and then recheck. If I don't worsen the solution, then I make the change. So if I have a smaller number of uncovered interactions or the same number, I'm going to make that change. Otherwise, reset it back and then try again. If I haven't met the goal, then repeat the procedure by swapping rows. Okay? So here's an example of CPHF that I was working on. The reason I chose this one is that if I eliminated a row, it would become the best node currently today. But so at the beginning, I had around 900 uncovered interactions, and then in the course of about 3 hours, I was down to 200. Currently, the best node for this particular CPHF is 40. And I found that a value today. It was stuck at 44 for, I swear, the last month, and then today, it went down by 4. I was almost ready coming here to say, the best node is 44, I don't know if it'll ever improve, and it improved today. So there's quite a lot not known about these things, right? Yeah.
Actually, that's undecidable, right? Or is it?
Well, it's not undecidable because I can just enumerate all possible CPHFs and then check every one.
Oh.
Yeah, it's not encoding of a Turing machine here. Any other questions so far? Okay. So yeah, there's quite a lot not known here, but here are some improvements that are the best known today that were found using the algorithm that I implemented. So the first column is the covering array that it will be generated from the CPHF. The second column is the number of rows that are best known from the CPHF that I made, and the former best known, and the change that I did. And so it's quite amazing that all of these results are with high strength, with strength 5, 7, 8, which are obviously going to have very large covering arrays. And so it's really nice, like in an example like 727, I was able to remove 800,000 rows. So instead of having 2.4 million rows, I have 1.6 million. And if you check, most of these are twice the best possible. I need b to the t, and it's almost 2 times that. So these are almost right at the absolute minimum that the CPHFs can produce. All right. So I'm just going to talk a little bit about the existing implementation. So I didn't implement the CPHF checking algorithm myself. It was done by Kaushik Sarkar, who was another student of my advisor who graduated last semester. And I implemented Postoptimization on top of this. Both implementations were written in Java, so this will actually be very important for the next talk. But both implementations were in Java. And just to give you an idea of how this is implemented is a 3-dimensional vector where I'll actually show you the code. So this is literally copied and pasted out of the code. So I have C, which is the CPHF that I'm considering, and the outer dimension is each of the rows. The middle dimension is each of the columns, and the last one is each of the entries within a given t-1 length entry. And just to give you a little bit of perspective, there was one paper published, and it's still in the review process, but it was at least submitted. And the thesis work published based off of this. And the really interesting thing is, this idea of CPHS was introduced in 2006, and no work was done until last year. So this really cool idea was given almost a decade ago, and it took a decade to actually do something really interesting with it. All right, so But for this post-optimization algorithm, the most important part is checking the number of uncovered interactions, or equivalently, checking whether the CPHF really is covering. And so that's the thing that's going to be slowing me down the most. And so what I'm going to tell you about is how long does it take me to verify, on average, each of these CPHFs using the existing implementation. So anyone want to guess for the first one, how long does it take? So I have 2 rows, 6 columns, strength 4, and 3 symbols. Anyone want to guess? Yeah.
5 seconds.
5 seconds, anyone guess? What was that? An hour? Any other guesses? It's actually way less than both of those. It's 11 microseconds. So I can check this roughly 100,000 times a second, which is actually really powerful for this one. Although I can't really improve these because there's a result saying that you can't make a CPHF into 1 row. So this really is optimal for that one, but I can check these very quickly. 2933 takes a little longer, 28 microseconds. Don't worry, it's going to go up really quickly. 41 rows, so it's not quite so small, but it does have a low strength 3, and so that takes roughly 3.5 milliseconds. Strength 6, so fewer columns, but higher strength, it takes a little longer, 4.8 milliseconds. 93 columns and strength 4, so it's starting to get up there, 1.5 seconds each time on average. 51 columns and strength 5, 3.6 seconds. 26 columns, strength 7, 35 seconds. And now we're starting to get into the times that were suggested earlier. Over 1,000 columns and strength 3 takes a little over a minute, so 1:20, I guess. 90 columns, strength 6, so really high strength and a moderately large number of columns. Takes about 40 minutes in general. And 5,300 columns and strength 3, around 2.5 hours to verify once. So that causes a little bit of alarm, right? If I want to even just check it, it takes over 2.5 hours to verify. I actually know some CPHFs that I don't even list here that take days to verify in general. So we need to do something about this, and quickly. So what I did is I re-implemented this in C++. So how many of you actually code in C++? Okay, so that's good. So you know that C++ has some performance benefits over Java, and I'm going to cover those next week. So I'm just going to talk about the basic structure and how I divide tasks. So I have a finite field thing. I need to do arithmetic over the field. I have this thing called a combination generator, which it provides the T columns that I want. And then when I ask it again, it provides the next set of T columns, again, next set of T columns. And so it turns out that this is the major bottleneck of the program, and we'll see that next week. I have the actual CPHF thing, so it has functions to say whether it is covering or not, number of uncovered interactions, that kind of thing. And the post-optimizer thing, and it has a CPHF thing, and it runs that algorithm I told you about earlier. So, and main CPP has a post-optimization object and just runs it. So pretty simple, just exactly the same ideas as we said. So here's the final slide, and so I know no one likes cliffhangers, but I'm the one giving a talk. I'm giving you a giant cliffhanger. So here are the times for Java that I talked about earlier. So it's pretty much the exact same algorithm, but with modifications and optimizations for C++. And so does anyone know how much this actually improved or worsened? Did it worsen? I don't think it worsened. So how much did it speed up, do you think? Like 10%, 20%?
I'd say by a factor of 100.
A factor of 100? Anyone else?
Factor of 10.
Factor of 10?
5.
5. All right, so in this particular case, Gabriel is the closest. It's around 8 times faster. And it's actually pretty amazing. Just the same algorithm, just ported to a different language, like barely any changes to the code other than the syntactic things, gives an 8 times improvement speed up.
That's, the Java is interpreted code though, right?
Yeah, so I'm going to cover that all next week.
Yep.
And there are other optimizations that even produce a larger improvement than the virtual machine, the difference between C++ and Java. What about 3, the next one, with strength 3? It actually goes higher. It's 21x times faster, which is it's just amazing. And it's going to amaze you as we go down even more. So strength 3 again, almost 20x times improvement. So strength 6, unfortunately strength 6 is not as powerful, it's only around 3x. Strength 4 is going to be around 8x every time. So this is 8.39x, actually almost exactly 8.3x every time. Strength 5 is going to be in the middle ground, it's around 5x. Strength 7 is going to be a little bit less than strength 6, around 2.69x. And so now is where the real amazement comes in. Strength 3, 20x times faster. Even with this large CPHF, it takes over a minute to verify, where my C++ program takes 4 seconds on the same machine, just by porting to a different language. I think that's pretty amazing. That's not the crazy part. Strength 6, this one isn't quite so amazing, even though it's strength 6. And next week we'll see why strength 6 doesn't perform quite as well as the other ones. But here's the amazing one. It gets a 20 times X improvement again. So instead of taking 2.5 hours, my C++ program takes 7 minutes. Yeah.
There seems to be some kind of pattern or correlation
Yes.
for any strength level of the performance improvement.
There absolutely is. As Patrick was saying, if you look at all the strength 3 ones, it's about 20x every time. If you look, well, there's only 2 examples of 4, but it's 8.3 in that case. Well, there's only one of 5, and so every example of 5 is about 5 times.
How much memory does this verification process take on these kinds of?
Very, very, very little. Other than the CPHF, it takes only I would say about at most a kilobyte more.
Okay.
I'm generating these T columns on the fly, believe it or not. And I'll actually discuss about that particular issue next week. But I think that's pretty amazing that just a simple translation to a different language gives such a huge speed up. And so I know you want me to cover why this happens, but that's the cliffhanger. So I'm going to leave that till next week. So are there any questions? Yeah.
How did you end up in this research?
How did I end up in this research? I was asking my advisor about what good directions in terms of covering arrays need to be done. And this was actually a course project that I did, but I extended it out into C++ territory. So if we actually go back, eventually go back, these results were from the Java implementation, not even the C++ one. So it's pretty amazing that we were able to accomplish so much with even just a slow program. But in terms of getting into the research, as you told me, hardly anyone was working on this. Actually, no one was at the time. And so I just looked at this and said, oh, these 2 ideas, post-optimization and CPHF, both of them independently are being studied, but never together. So I thought, okay, that's going to be a nice idea, and we actually do get really good results here, as I showed earlier. Any other questions? Yeah.
When you're talking about taking the existing covering arrays and extending them in terms of their columns, if you have an optimal covering array, and is it possible to then add a column and it still work, or would you have to extend the rows on an optimal covering array?
It depends what you mean by optimal. So it turns out, yes, it is true. For that Kleinman and Spencer thing I talked about earlier, where T and B are equal to 2, you can actually get to a very, very large number of columns and have the same number of rows. And so, like if, say, for for t and v equal to 2 and 3 columns, I have 8 things, let's say. I can extend that a few times, and then then it tells you what the next number, if you need to add 1 row, how far you can go next. And one of the references I'll have at the end is tables by my advisor, which have the best known covering arrays. And it tells you for a given number of columns, what's the best n so far, and then it makes a jump to the next row, the next number of rows. So if I say increase the number of rows from 16 to 29, then I only need 1 more row. So in between, so 17, I'll need 1 row, but 18 is still the best known, 19 is still the best known, 20 is still the same number in all of those. But you're right, you can, it depends what you mean by optimal though. Is it the number of rows or is it the number of columns in that case? Any other questions? Yeah.
And then for things that aren't like binary flags, like test on or off, what would be like a real world example of something that may have like 3 potential levels?
If you have, say, like user input field, these are more studied as combinatorial objects. So like I have these specific parameters. What is the smallest thing I can make? So that's a combinatorial type question. But you can have things like they can enter, say, Visa, MasterCard, American Express, those 3 options. Or maybe, so if you look in the literature, when they introduce these things, they always have a practical example. So maybe like you're testing whether an operating system works. So like Windows, Mac, Linux, those 3 options. And then you work with a certain browser. So Internet Explorer, Chrome, Firefox, let's say. And so you work with all those options and then you try to do the combinatorial test suite based off of that. Okay. Any other questions? So thank you for, oh, yeah.
It seems like a lot of the research that you're doing is like going towards the computational approach. Are there other paths that are going more towards like non-computational, like trying to find like properties of them in order to?
Yes. So I'm actually looking at that right now. So does anyone know what an affine transformation is? It's okay if you don't. So it's basically one of the constructions of covering arrays. There's a similar, we're trying to make one for CPHFs, is take a covering array and literally copy and paste another copy here. Well, all the interactions that are just in the original T columns, those are going to be still covering. It's the ones that that go across that are going to possibly be non-covering. So what you do is you copy and paste it down and then modify the array down here. And then we can guarantee that it is covering there. So for those, for CPHS, we're trying to look at what is called affine transformations. And what you do is you randomly, for a given row, just alter the entries by just multiplying by a value, then adding another one, and seeing the probability that it remains covering. But we don't have any results in that. As I said, all the results on CPHFs that are known are purely computational, which is the random extension method, which is adding random new columns or adding new random rows. Those are and post-optimization, obviously. So those are the 3 basic, best known computational methods for CPHFs. Any other questions? All right, thank you for having me. So next week, I'm going to talk about all the nitty-gritty details of my C++ implementation. So I hope you're all here for that. So thank you again for having me.